Today, we are going to be talking about deriving charge conservation. Now, since first year physics, we've been assuming that charge conservation is something we've observed. But we're going to go beyond that. We're going to derive it from two basic assumptions. These two basic assumptions are, one, energy is conserved in an isolated system, and two, we can set our potential equal to whatever constant we want infinitely far away from our charge distribution. So our charge distribution is going to be localized, which means that we can put some sort of surface around it and it closes all of our charge, and V equals V naught, and that can be any V naught we want out at infinity. All right, so with those two basic assumptions, we're going to start with a certain charge distribution, some physics is going to happen, and we're going to get a different charge distribution, and charge is going to be conserved. We're going to prove that. Okay, using conservation of energy, what we can start with is an expression that has all of the electric potential energy. So that means we've got Q1 initial, V1 initial, where V1 initial is the electric potential that charge 1 is experiencing, plus Q2, V2, and that is of course the electric potential that charge 2 is experiencing, plus all of the other charges in our system, and we are deliberately leaving that completely open. It can be any number of charges we want. The physics will stay the same. This is, of course, all of our initial electric energy. And when we have all of our initial electric energy grouped together like that, we can have all of the other types of energy grouped together as well. So, for example, we could have non-electric potential energy. So this would be gravitational potential energy, nuclear potential energy, anything that's not electric for every single particle that we have. And once again, it's completely general, not necessarily just two, which is what the ellipses are here for. All right, well, in addition to potential energies, we could also have internal energies. So the internal energies that we have and those are, once again, the initial energies. And then, of course, it's not just a matter of internal energies and potential energies. We could have things moving around, so there could be kinetic energy associated with this as well. We have an isolated system. Because we have an isolated system, no particles are going in or out, although particles could be created or destroyed. They're all going to stay inside of our system, and no energy is going to enter or leave. As we said before, this means energy is conserved, so all of this is going to wind up being equal to QA VA plus QB VB. This is going to be final. Now, note that we started off using 1 and we're ending using A. The reason for that is that we don't know whether the electron we're seeing in our final system is going to be the same as the electron that we saw in our initial system, or our quark, or our whatever particle we have. So we have to come up with a different convention, which means that A, we'll experience potential A, which is different from V1, potentially. QB, VB, which is different from Q2, V2, or Q1, V1. These are all different, but this is now our final electric potential energy, and of course our final electric potential energy is not necessarily the same as our initial electric potential energy, because our final electric potential energy could have had some sloshing back and forth of the energy from these different bins. So we could also have some non-electric potential energy, once again with the A, because it's particle A, non-electric B, and so forth. And then we can have our internal energies, oops. Of course, there can be more than just A and B. And things could still be moving, so KEA plus KEB plus dot, dot, dot. Fine. And of course, this equal sign right here in the middle says that you add up all this energy, it's equal to all of this energy. Note, however, the number of charges has actually changed, and that's going to be absolutely essential to the overall derivation of charge conservation that we are doing. Now what we're going to do is we're going to do a trick. We're going to do the kind of trick that makes mathematicians go, why are you bothering? And physicists go, ooh, fun trick. We're going to invoke a symmetry. And when we invoke a symmetry, really what we're doing is we're making what's known as a gauge transformation. There'll be more on that later. But we're going to describe the exact same physical situation with a slightly different set of mathematical variables. So, one way to think about it is we've got our electric potential here, but we've got a set electric potential at infinity, and we're going to change what our electric potential at infinity is defined to be. Another way to think about it is you put the whole thing inside of a Faraday cage, and you just up the voltage for the Faraday cage. The physics is exactly the same, whichever way you want to think about it. What this means is that when we start with our potential V1, V1 is going to wind up going to a new potential, V1 plus V0. And we didn't just have V1, we had V2, which will also go to V2 plus V0, and so forth for all of our initial electric potentials. Because we're making this gauge transformation, because we're changing the symmetry, we're making a different choice about our electric potential, we're going to wind up having to add the same V0 to our potentials after the fact. So VA also transforms in exactly the same way. VB will transform in exactly the same way. And so forth for all of our final electric potentials. We haven't changed anything about the physics. We also haven't changed any of the non-electric potential energy. Our gravitational potential energy is exactly the same. Our kinetic energy is exactly the same before and afterwards. All of our internal energies are the same before and afterwards. But our initial potentials and our final potentials are going to wind up being different now. This means that our expression for our initial will now become Q1 V1 plus V0 plus Q2 V2 plus V0, and so forth, dot, dot, dot. And for our final, we have QA VA plus V0 plus QB VB plus V0, and so forth and so on. Keeping in mind, all we're changing is the electric potential. Every other type of energy is going to be the same. So plus the same as what we had before, plus the same as what we had before. Of course, this is our same initial, and this is our same final. But these are going to wind up being equal to each other, just like they were before. With our gauge transformation, this change of potential at r equals infinity, what we've just done is come up with two equations. Now we're going to go back to high school algebra. So we have our two equations, and the first equation is just Q1 V1 plus Q2 V2 plus all of our other charges times the electric potential they all wind up having, plus all of the other energies that we have. And this is initial, and this is initial. And this is going to wind up being equal to QA VA plus QB VB plus all of our others. And this is going to be our final plus all of our other final. So that was the first thing we derived. Then we did this change, this gauge shift, and when we did that, we came up with a slightly different expression. So, this is not equal to this. However, all of our other energies are equal. So we can say all of our other initial energies, so this is initial, plus other initial. This initial and this initial are going to wind up being the same, even though this and this are not. So this is equal to this, but this is not equal to this. This, however, is equal to this. QA VA plus V naught plus QB VB plus V naught. And much like this, we still got our plus dot dot dot. And this is going to be final plus our other final. And of course, this other final is going to be exactly the same as this other final, because the only thing we changed was how we were looking at our electric potential. We have two equations, and going back to our high school or maybe even middle school math, we can subtract one equation from the other equation. Subtracting one equation from the other equation means an awful lot of things are going to wind up canceling out. Specifically, we've got this V1 term, it's going to cancel, Q1 V1 term, Q2 V2, and then on the other side, QA VA is going to cancel with QA VA, QB VB is going to cancel with QB VB, but also all of our initial energy is going to cancel with all of our other initial energy, and all of our final energy is going to cancel with all of our other final energy. So when we subtract this expression from this expression, what we're left with is Q1 V naught plus Q2 V naught plus dot dot dot. Every single charge we start with times V naught, the amount we shifted our electric potential. And this is going to be equal to QA V naught plus QB V naught plus all of the other electric charges that we end with. And of course, what you can immediately notice is that every single term has a V naught in it, which means Q1 plus Q2 plus dot 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 is going to equal QA plus QB plus dot dot dot. So the sum of our initial charges will wind up equaling the sum of our final charges, regardless of what physics happens, as long as our system is isolated. And we have the ability to change what the electric potential is at infinity. Those were the only two assumptions we started with, and we were able to get to charge conservation happens regardless of what nuclear process, what thermodynamic process, what electromagnetic process, what mechanical process happens. Charge is always conserved as long as you have an isolated system and that gauge symmetry. We started with just two assumptions. One, conservation of energy, perhaps the most sacred law in all of physics. The second thing we started with as our base assumption is that we can make this change about where we set our electric potential. As you go on in physics, you're going to see other symmetries get exploited in order to show other conservation laws. Perhaps we'll do more in another video. But for now, we started with those two assumptions, and what we concluded was that charge must be conserved regardless of the physical process This is a deep and profound insight. It also matches experiment. Experimentally, we've been noticing that charge is conserved no matter what. But it's nice to have a theoretical basis to explain why. And it's nice to know that it all comes from conservation of energy and this fundamental symmetry about the gauge invariance for the electric potential.